This video is the payoff for the past 2 hours worth of careful study. So, what have we learnt thus far? We learnt about aggregate analysis and why we should focus on the total running time of a sequence of operations that we do to a data structure rather than on simple worst case per operation analysis. We learnt how to do aggregate analysis. We learnt about the amortized design of algorithms, and we learnt about the potential method as a reasonably painless way to calculate aggregate running times. And then we had a digression into priority queues, which we used as a springboard for the Fibonacci heap, a very cunning implementation of the priority queue. But I said that to really appreciate what was so cunning about its design, we had to wait to see its performance analysis. Well, that performance analysis is what we're going to look at in this video, the amortized complexity analysis of the Fibonacci heap. Let's just jump straight to the punchline. Here's the answer. We're going to use this particular potential function and we're going to derive these amortized costs. Have a quick read just so you know where we're heading. Also, if you don't remember the details of the Fibonacci heap, in particular if you don't know what number of roots means or number of losers, then please go back and review the last video. Pause the video now, and when you've read all this, press play. So, how are we going to derive all this? Well, the first two operations, push and decrease key, we're going to show these are big O of 1, and that's just a pure piece of amortized analysis. All it comes down to is the potential function and how it fits in with all those very particular rules for the Fibonacci heap. The third operation though, pop_min, is a bit different. To get to this big O of log n, we're going to have to adapt the strategy that we used for analysing the binomial heap. In the binomial heap, we first figured out something about the shape of the heap. A binomial heap has a really rigid shape. It's made up of binomial trees, and binomial tree sizes are always powers of 2, and so it was easy to work out the size of the largest tree in the heap. It's got to be a tree of degree log n. That's why all the operations are big O of log n, because their worst case is always working on a tree of degree log n, whether we're processing child nodes, walking up the tree, or whatever it is we need to be doing. And for the Fibonacci heap, we're going to do basically the same thing. We're going to prove a nifty result about how many children each node can have, and the answer turns out to be log n, and this will be what gives pop_min its big O of log n complexity. By the way, do you see that little phi there in the base of the logarithm? That is the golden ratio. It's one of those achingly beautiful bits of maths where algebra and geometry and art all come together, and it has a deep connection with the Fibonacci sequence. And by the end of this video, you'll see what it has to do with our data structure. Okay, let's dive straight in with the complexity analysis. We'll start with the push operation. Here's the code. This one's really easy to analyze. It barely does anything at all. It just plonks the new node into the root list, and so its running time is big O of 1. But remember, we're doing an amortized complexity analysis here, so we want to calculate the amortized cost, C plus delta phi, where delta phi is the change in potential. So what's this term? Well, let's first remind ourselves what the potential function is. It's this function here at the top. Phi equals number of roots in the heap plus twice the number of loser nodes. So delta phi is 1. We increase the number of roots by 1. We haven't done anything to change the number of loser nodes. Okay, that was easy. The amortized cost, C plus delta phi, is big O of 1. Right, next operation. Let's now look at decrease key. Here's the code. Just pause the video and remind yourself how it works. Run through what happens when we call decrease key on the node labelled A in this picture. Pause the video and then press play when you're ready. First thing to note, there are two possibilities. Either we can just decrease the key in situ with no heap violation, or we've decreased it enough that there is a heap violation and we have to do some work to restore the heap. First case is trivial. We do O of 1 work. We don't change the shape of the heap at all, so delta phi is 0. So the amortized cost in this case is big O of 1. In the other case, there's a sequence of things that happen while we're restoring the heap. First, we slice node A away from its parent and dump A into the root list. This takes O of 1 work, assuming we've implemented all the child and parent pointers sensibly. And what about the change in potential? Well, we just put A into the root list, therefore the number of roots has gone up by 1, so phi increases by 1. Actually, hold up, we should be more careful than this. Could the number of loser nodes change? Yes, it could. If node A were a loser node, then according to our rules, line 40 of this code here, we would mark A as a non-loser once it gets kicked into the root list, and therefore the number of losers would decrease by 1, so the change in potential is actually -1 in that case. The difference between these two doesn't actually amount to anything much, it's all just O of 1 terms we're dealing with here, but still there's no excuse for sloppiness. And so the amortized cost of this phase of the operation is O of 1. And what do we do next? Well, we sliced out A and we dumped it into the root list, so now we have to worry about its parent, B, which is now a double loser. Actually, let's save time and think about this in aggregate. If there's a whole string of loser nodes sitting above A, let's say L of them, in this case L equals 2, then all of them will become double losers and all of them will get kicked into the root list. So the total amount of work we end up doing is big O of L. And what about the change in potential? Well, we're putting L nodes up into the root list, so phi increases by L, but we're also wiping their loser mark, so phi decreases by 2L, so the total delta phi is -L. And adding them together, the amortized cost of this part of the operation is big O of 1. Finally, we get to a node at the top of the chain of losers, node D in this picture, and then the iteration stops and we do O of 1 work. D has lost a child, so it gets marked as a loser, so the potential increases by 2. Unless, of course, D is a root, in which case we don't mark it as a loser. Anyway, once more, the amortized cost C plus delta phi for this part of the operation comes out to be O of 1. So, to summarize what we've learnt, in both cases, whether or not there's a heap violation, the total amortized cost is big O of 1. Great. Let's go on to the last operation, pop min. Here's the code. Let's step through it piece by piece. First, we'll cut out the min root and we'll promote its children to the root list. The work here is obviously proportional to the number of children, and the number of roots increases by number of children -1. The -1 is because we first removed a root before adding in all the children. To be meticulous about this, the number of loser nodes might possibly go down if one of the children were a loser because of that rule which says whenever you're kicked to the root list your loser mark is wiped clean. So delta phi might be as big as number of children -1, or it might possibly be smaller. Okay, but how many children are there? Let's remind ourselves of the shape theorem from the beginning of this video. We claimed that the maximum degree of any node in a Fibonacci heap with n items is less than or equal to log n to an appropriate base. So the number of children is big O of log n. So we've said C is big O of log n, delta phi is big O of log n. We add them together, the amortized work done here is big O of log n. Now we're beginning to see into the thought process behind the Fibonacci heap. To make this operation be big O of log n, we need the degree of a node to be O of log n, and so we can't allow ourselves to be in a situation where we have trees that are wide and shallow. That's the whole idea behind the loser flag construction. Anyway, let's proceed. The next lines of code do cleanup. They repeatedly merge trees whose roots have the same degree. And that piece of code deserves closer inspection, which we'll get to in a moment. But let's skip over it for now. After the cleanup, the last thing we do is we scan through the root list to find the tree with the smallest root, and we'll update min root. There's a magic phrase I snuck in here: scan through the cleaned up root list. Think of what the cleanup just did. It merged all trees whose roots have equal degree. Therefore, after cleanup, all of our trees have roots with different degree. And thanks to the shape theorem, we know that the maximum degree is log n. Therefore, this scan takes time O of log n. Okay, so let's recap. We've just shown that the total amortized cost of popmin is big O of log n. The only bit left to think through here is the cleanup phase. Let's look at it in more detail. Here's some code. This is how we might implement it. Let's step through an example to see how this code works. First, we'll declare an empty array called root array. This array will have one slot for each possible degree. And thanks to the shape theorem, we know exactly how big to make this array. We can have trees of any size from 0 up to log n, so let's declare an empty array of size log n plus 1. Next, we're going to iterate through the trees in our root list. Let's look at them in turn. First tree we come to, the root has degree 0, so let's put in slot 0 in the array. Next tree, the root has degree 1, so let's put in slot 1. Next tree, the root has degree 0, but hold on, slot 0 is already occupied. So we do what the cleanup phase is all about. We merge trees whose roots have equal degree. Now, can we put this into the root array? No, the slot it would go in is already occupied, so again we have to merge trees. By the way, when we're merging trees, of course we're merging them to preserve the heap property. That's the defining property of a Fibonacci heap, that all trees have to satisfy the heap property. That's why I made 4 be a child of 3. Okay, so now we can place this tree into the root array. And then move on to the last tree in the root list and stick that in too. Finally, the last line of the cleanup procedure says scan through the root array and update our root list to be a list of all the trees that we've ended up with. Great, that's the code. Now let's see if we can work out its amortized running time. First, let's set up some notation so we can account for all the work we're doing. Let's say let x be the number of trees we start with, let y be the number of trees we end up with, and let m be the number of mergers that we do in total. And let's just count up the aggregate amount of work we're doing. We have a loop over all the trees that we started out with, big O of x. For each tree we come to, we end up doing a certain number of mergers, lines 24 to 28. But let's not try to account for each of the trees individually. Let's just let m be the total number of mergers we do in the entire cleanup phase. So we spend time big O of m on these lines. And finally, we write out the new root list, and that's O of log n, the size of the root array that we have to scan through. Now, just a bit of tidying up the algebra. Here I've written the x term as x equals y plus m. The idea here is we started out with x trees, we did m mergers, and every time we merge we decrease the number of trees by 1. And so the number of trees we end up with at the end, y, is equal to x minus m. And lastly, as we said when we dimensioned the root array, the number of trees that we end up with, y, has to be less than log n plus 1. And finally, the big O notation doesn't care about constants, so let's just drop the 2. So this is our answer. The total work we do in cleanup is big O of number of mergers m plus log of n. And now for the amortized magic. Remember what our potential function is? It's the number of roots plus twice the number of losers. We're not doing anything to loser flags in any of the work here, so that part doesn't change, but the number of roots definitely does change. It decreases by 1 for every merge we do, thus delta phi is equal to minus m. Add these two together and we get total amortized cost of cleanup equal to big O of log n. This was a truly sophisticated analysis. We've just gone through the algebra here, and the answers sort of just dropped out, but how on earth could anyone have come up with all of this in the first place? This is a good point to step back and review what we did, and see if we can persuade ourselves that it had to be done this way. Here are the two big pieces of code, the pop-min cleanup and the decrease key. And let me highlight two big scary pieces in this code. In the pop-min cleanup, we had to work through the entire root list and merge trees, and the root list could have been huge. There could have been an uncontrolled number of mergers for us to do. And in decrease key, we had to work up through the depth of the tree, and it could have been very deep, and there could have been an uncontrolled number of loser nodes for us to work on. What I mean by uncontrolled here is that there's no simple way to bound these values, the number of mergers and the number of loser nodes. We could of course come up with a crude bound based on n. Obviously the number of mergers we do could potentially be as large as n-1 if our heap consists of a whole bunch of singleton trees, but that's not a tight bound because we'll never hit that worst case twice in a row. And so this is why we want amortized analysis. Amortized analysis is for exactly this sort of situation where we might have a lot of work to do in one call, but the tidying up we do will benefit later calls. And the easy way to think about amortized analysis is with a potential function. The interpretation here is we may hit an uncontrolled number of steps m, but if we pay for them in advance, then we're good. So if we just put £1 into our bank account every time we create a root, then we will have enough money to pay for the mergers that we're going to have to do sooner or later. And likewise, if we put money into our bank account every time we mark a node as a loser, we'll be able to pay for the uncontrolled number of steps in decrease key. In fact, we can even see why there's a factor of 2 in the potential function. If every time we mark a node as a loser node, we can anticipate first that we might have to kick it out of the tree and into the root list in some future call to decrease key. And second, now that that node has been put in the root list, we're probably going to have to do a merge with it in some future call to pop-min. So we put in £2 for every loser mark, enough to pay both of those bills. Okay, let's review where we've gotten to in this proof. We've found the amortized cost of each of these operations. It took a lot of care to do it right, but it was basically just diligent and careful counting. There's no cleverness needed, except for the cleverness of inventing the right potential function in the first place. It's a good idea to read through all of this complexity analysis in the printed notes that go along with this course, so you can see it all laid out. And it doesn't actually come to that much, it's just a page of working. This is the sort of amortized complexity analysis that you should be able to come up with by yourself once someone gives you a potential function to work with. And inventing the potential function did take some insight, but again, I hope you can see it didn't come out of the blue. It's sort of forced to be what it is if we're going to get these O of 1 and O of log n amortized costs. But what really does take out of the box thinking is this final piece, the shape theorem. And that's what we're going to prove now. In the exam, you'll definitely be expected to be able to do careful, detailed amortized analysis once someone gives you a potential function, and you'll also be asked to invent your own potential functions. But this shape theorem, it's so out of the box, it's non-examinable. I'm only including the proof here because otherwise you'll be left wondering where on earth does the name Fibonacci heap come from. Okay, so let's prove the shape theorem. Here's what we have to prove. In a Fibonacci heap with n items, every node in the heap has degree less than or equal to log n, log to base phi, where phi is the golden ratio. And here's how we're going to prove it. Pause the video, read through this shape lemma, and then once you've read it, press play. Let's first just remind ourselves what the Fibonacci numbers are. F1 is 1, F2 is 1, and to get each successive element in the list, you add together the last two, so F3 is 2, F4 is 3, and so on. Let's just illustrate what the lemma is saying on this example heap here. Take this singleton node. This singleton node has degree 0. The tree rooted at this node is just the node itself, so the size of the tree is 1. And the theorem says the size should be above or equal to f of 0 plus 2, i.e. f2, which is 1. So yes, the lemma did work here. How about this one? The root of this tree has degree 3, and the lemma claims the number of nodes in the tree, which is 8, should be above or equal to f of degree plus 2, i.e. f of 5, which is 5, so the lemma worked here also. Just one more example. The lemma doesn't just make a claim about root nodes, it makes a claim about every node in the heap. So let's take a non-root node, this one here. This node has degree 2, so the lemma says the number of nodes in this subtree should be above or equal to f4, which is 3, and indeed it is. Once we've proved this shape lemma, it's fairly easy to finish off the shape theorem. Here's the proof. We want to bound the maximum degree of any node in the heap. So let's start by picking some arbitrary node whose degree is maximum, call this maximum degree D, and let's just apply the lemma to this node's subtree. Obviously, the number of nodes in the subtree we're looking at is less than or equal to the total number of nodes in the heap, n. The lemma tells us that the number of nodes in the subtree is above or equal to f d plus 2, where d is the degree. Next, there's some maths about Fibonacci numbers. There's an exact formula for a Fibonacci number, and it's a funny formula here involving the golden ratio and the square root of 5. When I first learnt about this formula, it was my first introduction to matrices and linear algebra, and it completely blew my mind. How on earth can something so computational and discrete like Fibonacci sequence be related to continuous maths and irrational numbers like this? If you haven't come across this fact before, then I hope you'll enjoy learning about it as much as I did. Anyway, just a little bit of tidying. This formula tells us that fd plus 2 is above or equal to phi to the d, where phi is the golden ratio. So we've proved n is above or equal to phi to the d, and taking logs of each side, d is less than or equal to log n. Good, so that was just mopping up. The heart of the proof is inside this shape lemma, and the proof of it has two parts. Here's the first part. There's a definition and then a claim about the Fibonacci heap data structure. Pause the video, read these, and when you're ready, press play. To see where this claim comes from, let's step through the life of a node in the Fibonacci heap. Pick some arbitrary node somewhere in the heap, let's call it x. At some point in time, x might have been a root and it might have gotten merged with some other node, call it y. That must have happened if x has any children at all, because only root nodes are able to acquire children. And sometime later, x might have gotten a second child. Now, what we know about the merging process is that we only ever merge trees of equal degree. If y2 is the second child that x acquired, then x already had one child at the time, i.e. it had degree 1, therefore y2 must have had degree 1 also. And again, for x's third child, y3, we know that y3 must have had two children, because otherwise it wouldn't have been merged with x. So far we've just been talking about how many children each of the yi had when it was merged with x. But of course, nodes get shuffled around all the time, and some of the yi might have lost their children subsequently. But this is where the famous Fibonacci heap double loser rule comes in. If y2 loses one child, fine. If it loses two children, it gets kicked out of the tree. So if we're looking at x's children, we're looking at the yi that haven't been kicked out, therefore they are not double losers. So we know that each of them can have lost at most a single child. In general, child number I must have had I minus 1 children when it was merged, and it can have lost at most 1. Therefore, yi has at least I minus 2 children. Okay, so what we've shown is that node x satisfies the grandchild rule. But node x was just completely arbitrary. So every node in a Fibonacci heap at every instant of time satisfies the grandchild rule. Actually, what I've described here isn't quite a full description. It's just an illustration. When you write out the proof in full, you realize you need to be very careful with past tenses and subjunctives and accounting for children that x gained and then lost, then gained again, and so on. But that's too tongue-twisty for a video voiceover, and I hope this illustration is enough to give you the idea. Okay, we've proved the algorithmic half of the lemma. We've proved that our data structure's shape satisfies the grandchild rule. The next part of the proof is to tie together the grandchild rule and Fibonacci numbers. This part of the proof is purely mathematical. It's just about the shapes of trees. There's no more thinking through the steps of the algorithm. Pause the video, have a read of this claim, then when you're ready, press play. We want to say something about the size of a tree, assuming that every node in it satisfies the grandchild rule. Let's pick some arbitrary node with d children, say, and ask what's the smallest that this tree can possibly be. Let's define nd to be the smallest possible number of nodes in a subtree whose root has degree d, and let's find a recursive formula for nd. We know that any child yi has at least I minus 2 children. That's what the grandchild rule says it has. So the smallest possible number of nodes in that subtree is n I minus 2. That's just from the definition of n. N is the smallest number of nodes you can possibly have in a subtree. And if we add together the total number of nodes in the full tree, adding up the contributions from each of the children, the total number of nodes is above or equal to nd minus 2 for the leftmost child, yd, plus ... plus n0 for y2, plus n0 for y1, plus 1 for the parent node. In other words, we've argued that nd, the smallest possible number of nodes in this entire tree, is equal to nd minus 2 plus ... plus 1. So we've got ourselves a nice recurrence relation. There's just a tiny bit of algebra left before we spot that it's actually a very simple recurrence. First, let's just plug in the formula for nd minus 1. This is what we get. And we spot it's got precisely the same terms as the nd formula, except for the first. Therefore, nd is equal to nd minus 2 plus nd minus 1, which is exactly the Fibonacci recurrence relation. Therefore, nd is the dth Fibonacci number, or actually it might be offset. All we've derived here is the recurrence relation, not the base case. We should just work out what n0 and n1 are. They're 1 and 2 respectively, and that tells us the offset. It tells us that nd is actually fd plus 2. So, that concludes the proof of the shape theorem, and that concludes our analysis of the Fibonacci heap.